These are some generalized instructions about the critical value method involved in finding a conclusion for a statistical test. The critical value method is dependent on the type of test, so may it be a two-tailed test, a right-tailed test, and a left-tailed test. For a two-tailed test, the critical values are on both tails. So there must be one on the left and one on the right. For a right-tailed test, the critical value is on the right tail. For a left-tailed test, the critical value is on the left tail. So, doesn't matter which type of test you're performing, the area of the rejection region must equal the value of alpha. So always. So since I have two critical values, so you have two rejection regions. So that is a rejection region on the left for a two-tailed test. But its area will be alpha over 2. And then that is a rejection region on the right, right tail, with area alpha over 2. If you add the two areas, you end up having a total area of the rejection region equal to alpha. So in a similar way, if you look at the right tail and left tail test, you just have one rejection region. So the rejection region for a right tail test is on the right tail. And its area would just be equal to alpha. For a left tail test, the rejection region is on the left tail, with area equals alpha. So let's take a quick example. Suppose, as an example, if you assume that the test statistic has a normal distribution. Let's just say standard normal distribution. And let's look at all three cases. If you look at a two-tailed test, and if I assume that alpha is 0.05, for a two-tailed scenario, I must have rejection regions on both tails. So I have rejection region on the left, rejection region on the right, and the critical value is this number right there on the left and the right. So that is the left or negative critical value, and that is the right or positive critical value. 0, of course, is in the middle. And according to our problem, the area of this rejection region is 0.05 over 2, which is 0.825. The area of that rejection region is also 0.05 over 2, which is 0.825. You might wonder, why should I need to know about the area? If you know the area, then you can find the critical values. So the only way to find these critical values is by knowing what the areas are. And you should know where to place the areas because it also depends on the type of test. So this is a two-tailed scenario, therefore the rejection region is on both sides, each with area alpha over 2, and using that area I could find the critical value from a standard normal distribution using a calculator or using a formula. If you find the critical values, then you can obtain a conclusion. I would explain that as soon as I complete or sketch out a scenario for a right-tailed and a left-tailed test. So the second scenario is a right-tailed scenario. So you have a distribution on the right, you have a normal distribution and the rejection region is on the right tail. The area of the rejection region in this case is all of alpha, and in the example alpha is 0.05. And the critical value, I have only one, which is the right critical value. Most students tend to confuse themselves by placing a test statistic in the shaded region. So keep in mind, when we say rejection region, we say that part, that interval over the test statistic or below the test statistic, depending on the type of test. So the one in pink is my rejection region. The area is used to find that rejection region. And the last case is a left-tailed test. So for a left-tailed test, we could sketch out the distribution first. And since this is a left-tailed test, the rejection region is on the left-hand side, but the area of the rejection region is 0.05, which equals alpha. The critical value for the left-tailed test is right over there, which is the left critical value. And when we say rejection region, it's right over there. That is, the area corresponding to the rejection region is in purple. The rejection region by all means is on the real number line, and it's in pink. So how do we obtain a conclusion for each of these cases? So that's a left-tailed scenario, this is a right-tailed scenario, and the first one that we did is a two-tailed scenario. So attaining a conclusion is quite straightforward. Doesn't matter what test you perform, if the test statistic falls in the rejection region, then reject. No, it's that simple. So take a two-tailed scenario with arbitrary rejection regions. So I have a rejection region on the right hand side, rejection region on the left hand side. This is a two-tailed situation, and here There's a critical value, another critical value. So this is the negative critical value, it's the positive critical value. And suppose I place the test statistic there. In this case, the test statistic does not fall in the rejection region. So I will not reject the norm. So here, fail to reject norm. So the same test, two-tailed again. I have two rejection regions, one on the right, one on the left. Left critical value, right critical value. But this time, the test statistic falls right over there. So now, I would reject the norm. Now, what if I take one more scenario where I have a two-tailed test again. I'm quite particular about my normal distribution, so my apologies if I redraw something twice. So I have a rejection region on the left hand side, rejection region on the right hand side. Critical value on the right, critical value on the left, and hypothetically, let's say my test statistic fell over there. So in this case, I would reject no. Finally, I'll give you a minute for you to think about this. Let's say you're doing a right tail test. And a left tail test. So you have a right critical value for the right tail test, left critical value for the left tail test. Some funky distribution for the test statistic. Badly drawn normal distribution is the distribution of the test statistic. Hypothetically, I'm going to say that the test statistic for the right tail test is right over there, and the test statistic for the left tail test is right over there. So I'll give you about 5 seconds, or maybe 10. Think about the conclusion of the test using the critical value method for both cases. Should you reject the null, or should you fail to reject the null? Let's go. And silence is killing me, so I hope you know the answer. The one on the left side, which is the right tail test, you can see that the test statistic does not fall in the rejection region, so fail to reject null. And the one on the right hand side, which happens to be a left tail test, the test statistic falls in the rejection region, so you reject null. So this is a very generalized procedure for the critical value method. Of course, you have to find the test statistic, you need to have the sample and all, but This particular video is going to help you understand the critical value method in a very broad, generalized way. I hope you understand the critical value method after watching this video. Thank you for watching.